Hi, everyone. It's our pleasure to have Chuan today here to present his work. Chuan is currently an assistant professor at Shanghai Jiaotong University. His research interest is data-centric robot learning. He got his PhD degree from Tsinghua University, advised by Professor Yang Gao. During his PhD, he visited UC Berkeley, advised by Professor Kircher Yu. He also worked closely with Professor Dinesh Jayaraman at UPenn. Now I'll pass the stage to Chuan. Welcome.
Hey, hey, thank you. Thank you, King. Okay, it's really my pleasure to give a talk at RPL. Yeah. So let's start. Yeah, my name is Chuan Wen. I'm currently an assistant professor at Shanghai Jiaotong University. Yeah, let me briefly introduce myself. My research interests mainly focus on large-scale robot learning and visual motor control. Previously, I got my PhD degree from Tsinghua University, advised by Professor Yang Gao, and I was very fortunate to visit UC Berkeley in the fourth year of my PhD, working with Peter Abil and Xingyu Lin. We worked on some amazing topics such as policy learning from videos and cross-embodiment imitation learning. And 5 years ago, I was also very lucky to enter at Trevor Darius group, working with two postdocs, Yang and Dinesh. At that time, we studied causal confusion in imitation learning, the causal confusion problem in imitation learning. Yeah. Okay, let's start. Let's get started. Let's first see what typically data-driven robot learning pipeline looks like. Yeah, I know you are all the very experienced robot learning researchers. So I just briefly go through the overall idea here. The first step is data collection. This is what many research groups and companies are doing in recent years, especially in the recent 2 years. Inspired by the success of large language models, they believe stealing up robot data is the correct way towards a general purpose robot. Yeah, so they spend a lot of time and money to collect data by teleoperation, for example, the OpenX embodiment and the drive dataset. Yeah, after collecting enough data, we then began to train our policy with imitation learning, such as diffusion policy, ACT, VQBet, or etc. There are also some larger ones, which is broadly called the vision language action model. Actually, they are just imitation policy, just like what we did 5 years ago, but with a larger backbone. There are many VLE models, such as Pet Zero from Physical Intelligence, OpenVLA from Google, Groot from NVIDIA, and LBM from TRI. Yeah. And finally, we got our policy and deploy it on our real robot to evaluate whether it can deal with realistic pick tasks. Yeah, after recording, yeah, just like we record the success rates and then we write a paper and submit to the top conferences like RSS, Coral, and the project is done, right? Yeah, but actually this is current robotics research, but not the real robotics. Yeah, next, let me briefly go through what we have done in this pipeline in our group. We verify the data scaling law also exists in robotics manipulation. And we also propose flow-based video pre-training to achieve policy learning from videos. And then we also design a system with VR devices to collect human trajectories and verify that co-training robot and human data will enhance the motion level transfer. Yeah, for policy learning, we have a 3D foundation policy named IP3. We also propose efficient VLA in this year NeurIPS to accelerate VLA models. I think this is a really interesting paper because we found even if we prune a lot of parameters, the performance of VLA is even better. It's ridiculous, but it's true. Yeah, and we also try to integrate the tactile sensors into VLA models and this work is named the Tactile VLA. And I also have some robust imitation learning papers, which is really, really old work, around 2020 or 2021. Yeah. Although the data collection and policy learning have been broadly studied, the policy deployment process is usually ignored by us. We just ask a PhD student to sit sit next to a robot arm, executes a policy, resets the environment, and counts a number of success trajectories. But this paradigm is not suitable for the autonomy factories, yeah. Because the supervision is not scalable. It's just a stopgap for in the research lab. Because we can easily scale up the robots and data and policies. They just cost money, yeah. But it is impossible to scale up PhD students. Yeah, and I know this sounds like a joke, but this is what we are doing in the research labs. But in the future industry, it is impossible to have a PhD level worker sitting beside each robot. So how can we ensure robots will not cause damage to the environment? And how can we intervene in time when robots face uncertainty? These are very practical problems in the real world robot deployment. And on the other hand, the deployment is far more than just executing our policy. It's also a data generation process. I know there are many code base like Wumi or the diffusion policy or VQBase. They are code base implement to save the rollout trajectories during testing, but most of the data is not utilized for training, but just for the visualization or put the figures on paper. Yeah. So but we lost a lot of data in this process. So don't throw away any of your raw data, regardless of success or failure. These trajectories contain a lot of information. And in our recent work, we highlight the importance of policy deployment so that we can make the whole pipeline as a closed loop. Yeah. Yeah, to get this data flywheel spinning successfully, one crucial step is to leverage online data to achieve policy refinement. And I will introduce our recent two papers about policy improvements. One is about how to improve our policy with human intervention, and another one is a policy self-improvement with online exploration. Yeah, first let's start from our first work named Armada. The title of this paper is Autonomous Online Failure Detection and Human Shared Control Empower Scalable Real-World Deployment and Adaptation. Just as children, they usually make mistakes when learning new skills. Our robots also encounters errors and requires feedback to improve their policy. Uh, in this process, a human in the loop is the most direct and intuitive way for providing this to provide this such feedback. And there are many related works designing the human in the loop systems, including the very famous paper from RPL, Robot Learning on the Job from Hui Han. Yeah, which is also the inspiration for the title of this talk. Yeah, but the current human in the loop system are not sufficient enough. This is an example where a worker is monitoring a robot arm. We can see here I visualize the policy control bandwidth with a gray block, and the blue block denotes the human control bandwidth. We can see that the robot is running normally most of the time, so the worker just needs to take over control occasionally. So for the majority of the time, this worker just watch the robots and waiting for it to make mistakes. And this makes his job extremely boring and the workload extremely low. You can imagine you pay for a man to just sit there and just intervene the robot a few times in an hour. Hour. It's ridiculous. Yeah. Yeah. If we could have an autonomous monitor to detect failures of all the robots, the worker could devote all his bandwidth to intervention. So in this case, the human bandwidth will be fully occupied by the meaningful work, and we don't need to assign a worker to each robot. And this means we could achieve the automated factory workflow, where multiple robots are managed by a single worker. And this is a future factory in our brain, in our dream. Yeah. So in this framework, the first problem is uh, how we can detect online failures autonomously. Here we present float. Float means failure detection based on optimal transport. Yeah, first we assume we have a set of expert trajectories. I think this is a reasonable assumption that at least we need some expert demos to train our base policy. Yeah, then we execute our policy on the robot. Yeah, when the policy is rolling out step by step, we can compute the optimal transport values, which we call OT cost. We compute the OT cost between the extra trajectories and the rollout trajectory prior to the current step. That is lambda 1, lambda 2, and lambda 3 here. And then we utilize the success rollouts to autonomously calibrate a threshold. Here I denote as a capital lambda for the failure detection as a threshold here. Yeah, we utilize 90% quantile of the lambda values of all transitions in these success trajectories. And then we get a minimal one among lambda 1, lambda 2, and lambda 3 to as we name it a float value. We get a minimal value here, and then finally, um, we compare the float value with the threshold capital lambda to identify the failure. So this is a failure detection method based on the optimal transport. Here we visualize the OT cost with a growing curve. And we also visualize the threshold in the red line here. Yeah. When the OT cost exceeds threshold, we consider it is a failure case. You can see that when especially for the right column, we can see that when the error occurs, the OT cost will increase a lot and reach the threshold. And this method can successfully detect the failures, and in some safety sensitive tasks, we find it able to identify the early signs uh, before the policy really fails. Yeah, so it provides some advanced warnings. And then we integrate this online failure detection flows module into our multi-robot system. So the first step is if there is no failure detection, there is no failure cases detected, so we just continue the policy rollout. If not, we need to stop the policy here and then retrace back to the state before the error occurs. Yeah, here is a rewinding mechanism. We will automatically reset the robot to that state and ask the operator to reset the environment, referring to the image recorded at that time. Yeah, in our system, we will provide a reference image captured at that time before the failure occurs. Yeah. And when the failure is detected, it will be put into a message queue over a period of time. The reason for this message queue is because we consider it is possible that multiple robots might make mistakes in the same time. So this message queue is able to sequentially distribute the takeover instructions to the workers. So then the workers come, reset the environment, and take over the control to collect the correct trajectories. Yeah, and we record the human corrective trajectories into our replay buffer, and then update our policy by Dagger. Yeah, this is a Dagger-based method. No offline IO, no online IO, just a Dagger. Yeah, with this system continuously running, we deploy the policies, correct their errors, and fine-tune our policies. So the policy will iteratively improve over time. Sorry. Yeah, further question is that why we need this adaptive rewinding here? Yeah, because we want to ensure intact and informative episode with human corrective behavior. Just like what shown in this video, when a failure is detected, the robot will rewind and reset to this state, and the operators come here to reset in whole environment to according to a reference image, and then the human use a teleoperation device to take over the control and collect the correct trajectories, and then we uh, collect these corrective trajectories and put them into a data set to fine-tune our policy. And we find these corrective behavior is the most important in the dagger style algorithm. So let's have a closer look into our multi-robot system. We built a multi-robot system in our lab to simulate a robot factory. There are four flexible robots here, robot arms here, and one operator here. Just ignore these two guys standing here there because they are to reset the environment after the episode ends. Although I think it looks a little stupid, but we should have chosen some reset-free tasks. But we didn't have enough time to after we realized it before the deadline. Okay, we can see that all the robots are running autonomously. When failures are detected, they will stop and ask for human intervention, and we collect these data streaming into our data center, and then fine-tune the whole the policy. So this is a distributed robot factory here. Yeah, yeah, let me shut down. Okay, and then we evaluate our system on four tasks. The first one is pour marbles into a ball, and the second one is hang mag on holder and grass mango and put it into a drawer. And for the tower, these four tasks in the real world. We only have real world experiments in this world. The first experiment is to evaluate our online failure detection module, the float module. We compare with two existing methods, two existing failure detection methods. The first one is named stack, and second one is log. I don't know how to pronounce it. Just call it a log PZO. Okay. The stack is based on the temporal action consistency, which is to compute the variance between the overlap part of two action chunks. Yeah, because a significant larger inconsistency means the policy is more uncertain, which might lead to some failures. Yeah, another baseline I call it log PZO, which is based on the conformal prediction. The conformal prediction is a very classical algorithm in machine learning to estimate the uncertainty of a model. Yeah. So in this experiment, we let the policy runs until it fails or succeeds. Without any human intervention, we just roll out the policy to evaluate the online failure detection module. Uh, so, okay, and we count the true positive rate and true negative rate and the accuracy. And here the true positive rate means the the number of the times of the times of failure detector writes a warning signal during a rollout during a failure rollout. And while the true negative is failure detector never writes any warning in a success rollout. We can see that our method achieves significantly higher accuracy compared with these two baselines, especially the log PZO. You can see that uh, the true positive is always 100% and the true negative rate is always zero. This means that it's too sensitive that it will rise warning in each trajectory. So the recall is very high and the precision is zero. Yeah, and if you use this very sensitive online detection, failure detection in your robot system, it's pretty annoying. You need to intervene the robot in each trajectory. Okay. We also have an ablation study here. We try to include the stack, the action consistency evaluation like stack into our method. That is this one, ours, the float plus action. We found the performance, its performance is very similar to our float only result. This demonstrates our float is able to detect various failure modes without using any action information, but just care about the observation states. Yes, and our method is very robust to the variation in on initial pose and object spatial layouts. And then we we evaluate the policy improvements. We compare with series from Huihan's work. We can see that the online data collected by our human-in-the-loop system is in a relatively higher quality. This results in this will help make our system have better post-training performance. The policy is able to improve after each round of online data collection and the dagger updates. And we also show that the number of with the number of experiment runs increases, the human intervention rates will gradually decrease. This demonstrates the potential for extremely low human to robot ratio in the future. Because now the ratio is 1 to 4, but in our imagine, we think in the future, if the robot goes to work, we should at least 1 to 20 or 50 or even 100. Even in the whole robot factory, there's only one, just only need one worker to monitor all the robots. Yeah. So for multi-robot experiments, we aim to evaluate the policy generalization. We first appreciate the base policy from the expert demonstration, and then we deploy the pre-trained policy on scenario A, scenario B, and C for online data collection, and then we evaluate the post-trained policy on scenario D. Sorry. So we have three in-domain scenarios and one out-of-domain scenarios. Sorry. Yeah, this is to simulate a real-world multi-robot business where each robot may be deployed at we think maybe in the future each robot may be deployed at different workstations or even different factories. They will operate in very diverse environments, backgrounds, and lighting conditions. Yeah. Yeah, we would like to see whether these diverse online data could improve the policy generalization. Yeah, as an ablation, we conduct another round of deployment with the same pre-trained policy only on scenario A. Yeah. And we can see that our method Amada, consistently improves policy performance with multi-robot deployment. And we find the diverse deployment scenarios will enhance the policy generalization capability. It can make it perform robust in the unseen domains. So in conclusion, in this work, yeah, we propose an autonomous failure detection module to make the multi-robot system possible. And because we don't need to equip each robot with a human monitor, and we believe this is a scalable way to further scale up robot data, making the data flywheel spinning faster. Yeah, although looks like a cool system, the problem is there's still some problems. The most important one is that we still need a guy to hold the teleoperation device here. Especially this device, it is Sigma 7 from a company named the Fourth Dimension. Yes, that company. And this device is very expensive and it's not so easy. It's not very easy to be used by some normal factory workers. Yeah. So to achieve greater automation So in the second work, we investigate how to make the imitation policy improve itself by efficient exploration in the real world. And in this work, we propose the method named SAW, a new framework for our sample efficient robot policy self-improvement via unmanifold exploration. Okay. Yeah, because all of you are very experienced, robot researchers. I think you must have complained about your policy makes stupid mistakes. Yeah, and sometimes when we carefully study the data distribution, we usually find the correct solution should exist in the data distribution, especially for the policy classes which have very strong expressive capabilities, such as diffusion policy or the flow matching policy. But the policy fails to sample the correct one. Uh, yeah. So a very simple solution is to we just sample several times and record and just pick up the success trajectory as our final results, or we record the trajectory to post-train our policy again to reinforce the correct behavior. Yeah, this looks like very similar to the reject sampling in large language model, right? In LLM, usually we use a high temperature to roll out trajectories, and then select the success one to post-train our model. Okay, so this is a whole pipeline of policy post-training. Yeah, we aim to enhance the learned policy by enable robots to autonomously explore their environments and collect additional experience. And then we deploy this system on the real robot. But however, although we expect the correct solution should exist in the output distribution of diffusion policy, but we find diffusion policy usually suffers from mode collapse. It will generate some repetitive failures. So sometimes we cannot sample valid success trajectories, not even for once. So we aim to enhance the exploration capability of the policy by expanding the output distribution of diffusion policy. And another problem is that the search space is too large. I think it's okay to make your robot randomly explore in the Cartesian space, but it is too inefficient to find the correct solution in such a large space. So the second goal is to narrow down the exploration space. So in a high-level idea, the key to achieving sample efficient robot policy self-improvement lies in the effective exploration. So how can we make robots explore in the real world? This is a visualization of the rollout trajectory of our base policy. This is a rollout trajectory of the original diffusion policy, which is repetitive or even deterministic. And the lack of diversity makes it impossible to be utilized for policy improvement because there's no new information here. And in a traditional reinforcement learning, we just use action level exploration. For example, take the PPO as an example. We all know that each dimension of the PPO output is a Gaussian, and we randomly sample an action from that Gaussian distribution. And this is equivalent to direct ID noise to the action space. So, and some other exploration strategies such as um, like greedy, they are similar, just to perturb our output. Yeah, this will cause the output action make the output action temporarily inconsistent. like this is this zigzag trajectory. It is okay in simulators such as what we have done 5 years ago on Atari games, module call or DM control. We can deploy such very jerky trajectories. It is okay. But in the real robot setting, the temporal inconsistency is fatal. It will cause our robot trajectory to become very extremely jittery, and even damage the motor of each joint. Yeah, I think it's okay to deploy this trajectory on. I think on Franca is okay because it has a very strong PID controller with a very strong low pass filter. But if you deploy this trajectory on some small robot arms like Realman or Arc, maybe it will be broken. Okay. And another previous work named Sam, the authors proposed the model level exploration. They achieve this by inject noise into the latent embeddings of the observation encoder, and then they can get some diverse but still unstable trajectories. So in this work, we propose unmanifold exploration. Instead of adding noise on the action space or the latent space, we propose to explore with a constraint of the task manifold. Just like we only explore on this manifold, and otherwise go away from this direction or something. Yeah. Yeah. Uh, okay. Yeah, the core idea here is to get the exploration within the manifold. This will generate valid actions rather than some jerky ones. Okay. Yeah, and here is our high-level idea. We all know existing exploration methods typically rely on random perturbation, which can drive the policy of the task manifold, leading to some unsafe and even erratic motions and results in the ineffective exploration. So to address this, we propose this unmanifold exploration, which constrains the exploration to the manifold of valid actions, ensure some safety and effectiveness, and but supports a diverse behavior generation in the meantime. And then we merge the online collected trajectories with the actual demos to further refine our policy. Yeah. So next, we briefly introduce how we get the task manifold here. We introduce an information bottleneck into our policy to get a well-shaped latent space, which we call this latent space Z. Why we call it well-shaped? Because our training objective includes these two terms. The first term is to make the latent embedding contain the essential information to learn the correct action. Yeah, this is just to maximize the mutual information between the latent space and the output action. And the second term is to minimize the mutual information between the latent embedding Z and the observation input O. This is to make the latent space as compact as possible. We want to remove all the confounding information and the spurious correlations from this latent space to make it a very competitive and informative and well-shaped latent space. Yeah, so that we can ensure the exploration happens on task relevant factors rather than other random exploration on irrelevant factors. And this mutual information objective can be converted into a variational formulation. The first term is imitation learning loss, and the second term is a KL regularization, which is to make the latent space as a Gaussian model. So in this framework, we first encode the input observation O into a compact a latent space Z, which and this Z uh is a mixture of Gaussian and this space. Yeah. And then we explore in the latent space by randomly sample ZT within this Gaussian distribution here. And this alpha is to control the exploration magnitude. And then we decode the action from the sampled ZT here. Okay. Yeah. We implement our method as a plugin module on top of a diffusion policy, leading to this is a two-stream architecture. And the upper one is a base path, ensures the main policy remains unchanged. And the and the lower one, the exploration path generates very diverse action proposals through some structural sampling in a layered data space. And during training, each path is optimized by a separate loss function. And here is a stop gradient layer here to explicitly separate the gradient flows between them. So this is to ensure that the we introducing the exploration mechanism, it does not hurt the base policy performance. And during deployment, the robot can switch between these two modes, switch between the standard execution in the upper path and the active exploration path in the lower path. Okay. Yeah. So next, let me show some experiments here. We evaluate our method on real-world robotics manipulation tasks. And this is a Mark Hanning task. We visualize, let me play it again. We visualize the action trunk proposals during execution. We can see this is a base view and this is a wrist view. And in each step, we visualize all the a lot of action trunk proposals here. And we can see they are very diverse, represent some different action modes here. And we can also see that the action trajectory is smooth, relatively smooth, much better than some very jerky trajectories. Okay, and here are some more testing trajectories. By randomly exploring within the task manifold in the real world, we can always find a success trajectory and then collect it in and merge it into our dataset and then reinforce the correct behavior. And we can iteratively make our diffusion policy, make the distribution of the diffusion policy as sharp as possible to make it can always sample the correct solution. Yeah, here are some two more real world tasks, including bread loading task and lamp capping task. Yeah, some relatively fine-grained task. We can see the generated exploration actions are very diverse, but not very random and jerky. Okay, if you are familiar with VAE literature, variational autoencoder literature, you must know that the beta VAE has a very good property named disentanglement. And our experiment here also shows that our beta VAE like latent space naturally disentangles task relevant factors into several distinct dimensions. And we find each of them responds to a specific pattern of our behavior pattern. Yeah. And here we only visualize the dimensions with very high SNR, the signal noise ratio metric. And we also have one visualization for other dimension whose SNR is negative. We can see that Each of the dimension represents a very specific action pattern, and especially for this one, the last one with negative SNR metric value, we can see the exploration action chunk are not as diverse as other dimension. So in this experiment, we only sample in each dimension separately and keep other dimensions unchanged to visualize this. We can see uh, this entanglement property can provide more informative trajectories during exploration. And this property also enables human-guided exploration, where we can steer the exploration towards their desired directions by simply select action proposals without the need of teleoperation devices. And if we do this, it will further improve the sample efficiency and the controllability. So in this table, we can see that we compare with two baselines, the naive diffusion policy, and the second one is SIME, the model level exploration method. And the third and the fourth one is ours. The third one is the vanilla soul. We just randomly explore on the task manifold. And the fourth one is we have human steering by just we visualize a lot of action proposals and make the users to select one the best trajectory you think by the mouse. Yeah, we can see that we can achieve extremely high sample efficiency, and we can consistently achieve higher success rates and smoother motions, and reduce the rollout trajectory. Sorry, to reduce the number of rollout trajectories. This highlights the online exploration as it is a principal approach to sample efficient robot policy self-improvement. And we compare with action proposals generated by a diffusion policy, SAM, and our method. You can see our trajectory is more diverse and more and smoother, especially compared with SAM. You can see if you deploy uh, these tricky trajectories on actions on some very cheap robot arms, it will definitely it will jerk you a lot. Yeah. If you also visualize the trajectories before and after policy updates, we can see that after refining with online exploration data, the policy is able to predict the correct action here. Okay. So, and to further investigate the effectiveness of our method in multi-round policy self improvement, we also conduct some additional experiments on these for vision-based manipulation tasks in from robot mimic, and we found the results show that our method exploration method consistently outperforms the previous approaches across these four tasks, and we can get some substantial performance gain with fewer environment interactions. Okay. Okay, I think that's all. Thank you very much for having me today. If you have any questions, please let me know. Okay. Sorry, I can't hear you guys.
Can you hear us?
Yeah, okay.
Okay, nice. It seems that in your Dagger setting, after you train a policy and you roll out and you use reject sampling to recollect those successful trajectories during rollout and retrain the policy, that's right?
Yeah.
And do you think during deployment those failure rollouts are also valuable?
Yeah, of course, but uh, most of students in our group have a very struggling time on offline IO, especially for the CQL and the IQL. so too hard to make it work on the real robots tasks. Yeah.
I see. What's your opinion on learning from those failures?
Yeah, I think of course we should make it work in the future. But now I think there are some theoretically or the same system problem in the real world robots. Actually, they can work in the simulation, right? We can deploy it on the robot mimic or mimic gen, and they performs really good. But in the real world, robotics in all the infrastructure is not suitable for the iterative policy updates, and the sample efficiency is also very low, and the offline IO itself is not stable enough. So I believe in the future, the offline IO algorithm can make the failure trajectories useful. Yeah.
Okay, thank you.
Hi, Chuan. Thanks for your talk.
And
And I have several questions. For SOE, what's the number for collecting the improved rollouts? I mean, uh, uh, you do exploration during the base policy rollouts, right? Well, so what's the
yeah.
number for collecting those? Yeah.
Yeah, here we show the raw numbers here. Actually, for each task and for each initial post, we I believe we roll out the policies for 5 times, and once we get one success trajectory, and then we complete this initial post and switch to next one. So here we demonstrate we show the total rollout numbers here, and we can see um, our method can has like I think it is because our exploration strategy is more efficient. We can easily get a success trajectory, so we can early stop the whole pipeline. So in total, we have around 20 to 50 rollout numbers.
Why is the division policy performance decreased after improvement?
Yeah, because although the diffusion policy will suffer some mode collapse problem, but it still can. The mode collapse is not always occurs. Sometimes it occurs, and most of the time it can still get some successful trajectories, and you can still make the policy improvement work. But the sample efficiency is a little bit lower.
I see. And about the project of Armanda, uh, why, I mean, how does the optimal transport cost compare to the like progress value function? I mean, utilizing progress value function, you can also somehow adjust it to failure detector. I mean,
Yeah, that's a good question. We didn't make the progress value function work, actually. Yeah, I think this I'm not sure what kind of progress value function you mentioned here. If you means the VIP method from JSON must work, I think it's a little. I'm not sure whether it can work, but we didn't make it work in our system. And other online collected data to like a GAL-like method, if you train a GAL on this method, and the the value function itself is not trustable, so it will also cannot make it work. And we find the most robust method is the optimal transport. If you are familiar with the work from the Real Pinto's paper, I, th- I believe that the title is Watch and Match, or some that paper they use optimal transport for the inverse RL, and it is significantly better and more stable than the Gale-like method.
so how about using the embedding of some VLM? I mean, just pre-trained VLM. the embedding.
Oh, I see. Oh, I see. I see. You mean the GVL paper, the generative value
Maybe
on
I'm not sure. Uh,
oh, we didn't compare that. In our recent another paper we compare with GVL, like paper the VLM paper. I think it can briefly in a very coarse level you can get the progress, but I don't think it can. First, the computation cost is too high. If you compute that in each step, uh, your system is the delay is too high, and you can make it in a real-time system, right? And especially for the continuous control, and yeah. I think there are some infrastructure problem, and I don't think the current VRM is strong enough to capture the value. I still think the value is a little tricky in this coming in robotics.
Yeah, actually, the reason I asked this is because optimal transport cost seems to be will be very limited to the distribution of
Yeah.
expert trajectories. So maybe the generalization of float is I'm wondering about that. I'm not sure.
Yeah. I agree. So in the next step, I asked that student to explore some general purpose value or general purpose reward learning method. Yeah. Yeah, for this paper, this is just a system paper. It's we have some very suffering time on the communication delays on the multi-robot system, and make it work is not so it's not trivial. Yeah.
Thank you.
Thank you for a great talk. So I'm wondering for the Amanda paper, you mentioned that the adaptive rewinding is like improving the data quality and helps learning. So I wonder, is it because it removed the failure segment, or is it because it includes the recovery segment, so that it knows like how to improve from these states?
Oh, yeah, that's a good question. I think the answer is later one. Yeah, because we think even if you remove all the if you don't have the rewinding method here, and you can have some strategy to filter out all the failure behaviors, transitions in your data. But we think this still cannot effectively improve your policy because the most important one is the transitions, a few transitions just before your failures occurs, and and yeah, if you remove that part, it will there's no new information here. Yeah, but the human corrective data information is more important. So they provide very direct supervision to these critic transitions. I think there are some similar mechanism in Huihan's paper, in the series paper. They have some to predict the human delays before the human intervention transition, and they will remove the previous or emphasize the a few steps before this point. I forget the details, but I think there are some similar ideas from other papers to get the corrective behavior.
Thank you so much.
Any other questions? If not, thank you very much, Chuan. Thank you very much for
Okay.
talking time, and we'll see you in the one-on-one conversations.
Okay, thank you.